Hello everyone. So we'll continue our discussion of probabilistic Turing machines. Today we'll look at probabilistic Turing machines which have one-sided and zero-sided error. So I'm going to start by mentioning what we mean by one-sided and zero-sided error machines and how do they compare with whatever we have seen about probabilistic Turing machines so far. So the class BPP that we saw had two-sided error. So what do we mean by two-sided error? So what it means is that if the string X belongs to the language, even then there is a probability that the machine might give a wrong answer, the machine might reject. And if does not belong to the language, then also there is a probability that the machine might accept. So in both cases, there is a small probability that the machine can make a error. So this is what is known as two-sided error. Now, what if we allow only one-sided error? Okay, what if we don't allow any error to happen on either when X is in L or X is not in L? What kind of a complexity class do we get, and how do they compare with the two-sided error classes? Okay. So we define the class RTIME T of n analogous to DTIME T of n as follows. So a language L is said to be in RTIME T of n if there is a probabilistic Turing machine M running in time T of n such that if X belongs to L, then the probability that the machine accepts is greater than half. And if X does not belong to L, then the probability that the machine accepts is 0. Or in other words, the probability that the machine rejects is 1. Okay. Now, if you compare this definition to the definition of BP time T of n, you would realize that in BP time T of n, there is a probability of an error in both sides when X is in L and when X is not in L. Here, when X is not in L, we do not allow any error to occur. So when X is not in L, the machine always gives the correct answer. Now, the class that we get by looking at RTIME T of n when T of n is polynomial is the class RP. So this is analogous to the class BPP for one-sided error machines. And now we can define the complement of this class. We can define the class coRP as the set of all languages L such that the complement of L belongs to RP. So what this means is that if we have a language which is in coRP string, if a string is in the language L, okay, then the coRP machine will always accept that string. And if a string is not in the language, then the coRP machine will reject with probability greater than half. So one small point that I want to make before we proceed forward is that although here we choose the number half as a constant, okay, one can actually arbitrarily increase this probability by a significant amount, or by let's say 1 minus 1 over a polynomial. Okay, so I can always by repeating the same computation, I mean by basically running the same input on the machine again and again, okay, and by taking, so if the machine is, let's say, so suppose I take an RTIME machine which has these parameters, that is if X is in L, then it is probability of accepting is greater than half, and if X is not in L, then the probability of accepting is 0. So if I run this machine again and again, and whenever I have a yes answer, I just halt and output yes. Whenever I have a no answer, I keep on repeating this experiment. So if we actually repeat this experiment a sufficient number of times, one can show that the probability can be brought very close to 1, okay, the probability of correctness, or in other words, the probability of the machine making an error will be very small. So this actually we will be discussing in our next lecture more thoroughly when we talk about strong BPP and weak BPP and how we can use Chernoff bound to improve their, show that these classes are equal. Okay, so coming back to the class RP, or coming back to this definition of RP. Next is that one can easily show that RP is contained in BPP and coRP is also contained in BPP. So this actually follows directly from the definition. Okay. So in BPP, although here we have just greater than half, in BPP we require it to be greater than 2/3. But as I said that by just running this a few times, one can increase the probability of correctness to greater than any constant. And the last relation that I would like to state is that RP is contained in NP is contained in the class NP. And this also actually follows by definition, because just observe the following, that if X is not in L, okay. So think of a probabilistic Turing machine as a Turing machine where it's a non-deterministic Turing machine. And so whenever the probabilistic Turing machine does a coin toss to decide which direction it wants to go to, the non-deterministic Turing machine also basically does the same thing. It non-deterministically chooses which direction it wants to go to. Now, if X is not in L, then observe that no computation path of this machine accepts, which is exactly what a non-deterministic machine should do. On the other hand, if X is in L, here what we have is that at least half the many computation paths accept. In other words, at least one path definitely accepts. It's much, much more than one. So therefore, a probabilistic RP machine by definition is also an NP machine. Because if the input is in the language, we have at least one accepting path. Okay. Next, we move to zero-sided error. Okay. So in BPP, we had errors in both sides. In RP, we had error only in one side, RP and coRP both. Now, what do we mean by zero-sided error? Okay. So zero-sided error machines are probabilistic Turing machines that do not output the wrong answer ever. Okay. So if it does not output the wrong answer, then what do we mean by probabilistic? How is it a probabilistic? So here, what we allow is that the machine might output a I don't know answer with a small probability, or a question mark output with a small probability. What do we mean by that? So formally, if I want to look at it, so a language L is said to be in the class ZTIME T of n if there is a probabilistic Turing machine M running in time T of n with outputs from the following set: 0, 1, and question mark. Okay. So it will give three types of output. Now, if X belongs to the language, then the probability that the machine accepts is greater than half, and the probability that the machine rejects is 0. The machine will never reject. Okay. So this is what we mean by saying that the machine will not give a wrong answer. Okay. So what it does in the remaining computation paths is that it just outputs question mark. Okay. So in at least half the fraction of the computation paths, it outputs 1 and or it accepts, and in the remaining computation paths, it just output question mark or I don't know. Similarly, if X is not in L, then the probability that the machine rejects is greater than half, and the probability that the machine accepts is 0. So once again, if X is not in L, then on more than half the fraction of the computation paths, the machine would reject, and on the remaining computation path, it again outputs I don't know. Okay. So it will never give a, if X is in L, it never rejects, and if X is not in L, it would never accept. So the polynomial time analog class of ZTIME T of n is known as ZPP. Okay. Now, what is the relation between these classes BPP, RP, and ZPP? So we have already seen that RP and coRP both are contained in BPP by just the definition. And if we look at the class ZPP, again observe that ZPP is actually contained in the class RP. How do we show that it is contained in RP? So we just have to make one modification. So I'll just come to that in a moment. So in fact, one can show that ZPP is contained both in RP and coRP. Okay. So relation between ZPP and RP. So what one can show is that not only is ZPP contained in both RP and coRP, actually ZPP is exactly equal to the intersection of RP and coRP. Okay. And this is it's an easy result, but nevertheless it's an interesting result. Okay. So how do we prove this? I'll just give a proof sketch. Okay. So first we show that ZPP is a subset of RP intersection coRP. Okay. So given a ZPP machine, we show an equivalent RP machine for that machine. Okay. And how do we build that RP machine? So we build that RP machine by changing the question mark output to a reject output or zero output. Now what happens in this case? Just analyze. So if the ZPP machine was accepting, so suppose if I had an input which was in the language. Okay. Now we know that the ZPP machine accepts with probability greater than half, and the RP machine also now accepts with probability greater than half, because we are not changing the accepting criteria over here. On the other hand, if we had an input X which was not in the language, then the ZPP machine was rejecting it with probability half, and it was going to the question mark output with probability, with the remaining probability. And now what happens is that because I am changing question mark to 0, the ZPP machine will always be rejecting if X is not in L. Okay. So therefore, this shows that the ZPP machine can be converted to an RP machine by this kind of a modification. And analogously, you can also convert a ZPP machine to a coRP machine. Okay. So this proves that if a language L is in ZPP, then it also belongs to RP as well as coRP. Okay. So it is in RP intersection coRP. Now, what about the converse direction? So the converse direction is, suppose if I have a language which is in RP intersection coRP, how do we prove that it is in ZPP? Okay. So let's say that a language is in RP intersection coRP via the machines M1 and M2 respectively. So M1 is a RP machine for L, and M2 is a coRP machine for L. Okay. Now, given an input X, okay, how do we build the ZPP machine? So given an input X, first what we do is we run X on the machine M1. If M1 accepts, then we just halt and accept. If M1 rejects, then we run X on the machine M2. If M2 rejects, we again halt and reject. Otherwise, we output question mark. Now verify that if X was indeed in the language, okay, then the machine M1 always accepts with probability greater than half. Therefore, your entire construction also accepts with probability greater than half. On the other hand, if and it accepts with probability greater than half, and it would never actually reject. Okay, because if X is in the language, M1 would M1 might reject. So if M1 is rejecting, you are anyway going to M2, but M2 would never be rejecting because M2 is a coRP machine. M2 would always accept if X belongs to the language. Okay. So therefore, yeah, so M2 would always accept if X belongs to the language. So therefore, the machine accepts with probability greater than half, and for the remaining probability it would output question mark. Okay. And similarly, if X was not in the language, analogously one can show that again the machine will give the correct answer. So yeah, I'll just leave this sketch, I'll just leave the complete proof to you as an exercise. In fact, I have the following exercises. So firstly, show that ZPP is contained in BP, BPP. Okay. Or yeah, so how does one prove this? Next exercise is give a formal proof of the result that I just mentioned. So the one in the previous slide is just a proof sketch. You have to actually modify it a little formally, and then you have to argue that ZPP is RP intersection coRP. Of course, you also have to argue that whatever construction you are giving, it runs in polynomial time. The third exercise, in fact, the most interesting exercise, is to show this alternate definition of ZPP. Okay. So one can alternatively define ZPP as the class of languages for which there is a deterministic Turing machine that runs in expected polynomial time and always produces the correct answer. Okay. So what this means is that for some inputs, the machine can take longer time, longer than polynomial time. It can actually take maybe even exponential time. But on an average, the Turing machine runs in expected time. Basically, if I take an average over all inputs, then the running time of the Turing machine is polynomial. So this proves that this is a alternate definition of ZPP. In other words, if you take a language that is in ZPP by the previous definition, then that language is also in this class that I have defined in this third exercise. And if you take a language in this class, then it is also in ZPP. Both directions you need to show. Okay, so that is all that I had for this lecture. So, thank you.